Hello everyone, welcome to the second lecture. The plan for this lecture is as follows. We will discuss the fundamental problems addressed by cryptography, namely the key agreement problem and the secure communication problem. Then we will discuss the various types of cryptographic primitives, namely the symmetric key primitives and asymmetric key primitives. And then we will start our discussion on symmetric key primitives, where we will see the syntax of symmetric key encryption mechanism and informal security definition, and then we will finish the lecture with Kirchhoff's principle. Right. So, if you remember, in the last lecture we discussed that the central problem addressed by cryptography is that of secure communication, and in it turns out that secure communication is actually solved by solving two core problems, and the first core problem is that of key agreement. So, in the key agreement problem, the scenario is the following. We have two entities, a sender and a receiver, who do not know each other and who do not have any kind of pre-shared information, and they are meeting for the first time. And the requirement for a key agreement protocol is that, as per the protocol, the sender and the receiver should talk to each other over a public channel, and it should be guaranteed to the sender that indeed it is talking to the receiver and vice versa, and at the end of the protocol both sender and receiver should output a common key k. The security requirement from the key agreement protocol is that even though the sender and the receiver are talking publicly, and if there is a third party who is actually eavesdropping the communication or noting down the entire communication which is happening between the sender and the receiver, then the third party should not be able to figure out what exactly is the key which sender and receiver are going to output at the end of the protocol. So, it is like saying the following, that if I consider a class and the key agreement protocol should require that if I want to agree upon a key with a particular student, then using the key agreement protocol I should shout something in the class, and in response that particular student should shout back something to me, and using whatever I communicated to him and whatever he communicated back to me, both of us should be able to compute a common key, and no one else in the class who have actually seen the actual messages that I have communicated to that particular student and that student has communicated to me should not be able to figure out what exactly is the key that myself and that particular student are going to output. That is the first core problem addressed by cryptography, and this will be the theme of the second half of the course, where we will see how using public key cryptography which we can solve this key agreement problem. The second core problem which is addressed by cryptography is that of secure communication, and here the setting is as follows. We imagine that sender and receiver now have a secret key k which has been agreed upon by some magical mean, in this context actually by running a key exchange protocol. So, we imagine that sender and receiver have executed a secure key exchange protocol, and as a result they have a common key already available with them. Now, using the common key, the goal of the sender and the receiver is to talk over a public channel such that the confidentiality of the communication and the integrity of the communication is ensured. By confidentiality I mean any third party who do not have the knowledge of the key should not be able to figure out what exactly are the contents which sender and receiver are exchanging to each other, and by integrity I mean that if there is a third party who actually intercepts some of the communication and tries to change the contents of the messages, then it should be detectable at both the ends. So, that is the second problem, the second core problem addressed by cryptography, and this will be the theme of the first half of the course, namely symmetric key cryptography, where we will assume that somehow the sender and the receiver have already agreed upon the key, and our goal will be to solve the problems of confidentiality and integrity. So, roughly in cryptography we use two kinds of primitives. The first kind of primitives are the symmetric key primitives, which are also called as private key primitives, and here the same key is going to be used by both the sender as well as the receiver. That is why the name symmetric key primitive or private key cryptography. Symmetric because it is symmetric in nature, the same key is getting used at both the sender's end as well as the receiver's end, and the name private key cryptography because the key k which is common to both the sender and the receiver is going to be private, it will not be available in the public domain. Now, there are both pros and cons of these kind of primitive. The good side of these primitives is that they are computationally very efficient in practice, And the downside of these primitives is that the key agreement is going to be a big issue. That means, all these primitives works under the assumption that the common key has been already agreed upon by some magical mechanism, and which is a big assumption. So, ensuring that both sender and receiver have the same key is the challenging task. That is a downside of these primitives. The second kind of primitives are called as asymmetric key primitives or public key cryptographic primitives, where the primitive is operated with two keys. One of the keys, which is the public key, will be available in the public domain, whereas the other key, namely the secret key, will be available only to one of the entities, or in the context of encryption scheme, it will be available only with the receiver. That means, this has asymmetry in nature, that is why the name asymmetric key primitive. And the reason it is called public key primitive is that one of the keys is available in the public domain. Again, it has these kinds of primitives have both plus as well as the downside. The good side about these primitives is that you do not need any kind of key agreement. That means, if I take a public key encryption scheme for instance, then there is no requirement to do any kind of key agreement. Whoever wants to encrypt a message for me, it can take my public key, which will be available in the public domain. So, I do not need to explicitly agree upon a key with that particular sender. The downside of these kind of primitives is that they are computationally inefficient. That means, the amount of computation which are involved in this kind of primitive is of several orders of magnitude compared to the computation required in the symmetric key primitives. In practice, we use a combination of both. So, when we will be winding up our course and we will be discussing the real world protocols such as SSL, we will see that how we combine both these two primitives to get best of the both world. So, now let us start our discussion on private key or symmetric key encryption schemes. So, on a very high level, the goal is the following. The setting is as follows: we have a sender and a receiver, and by some magical mechanism we assume that a random key has been agreed upon between the sender and the receiver. So, I denote the key as k, which is actually going to be a bit string. Now, sender is interested to send some message m, which is again going to be a bit string, and in the cryptographic jargon we call this string m to be the plain text. Now, using the key, sender is going to use an encryption algorithm which takes the message and the key as the input, and it produces another bit string denoted as C, which is the cipher text or the scramble text, which is going to be communicated over a public channel to the receiver. At the receiving end, receiver is going to take the cipher text, which is a bit string, and the key, which is the same key with which the sender has operated the encryption process, and it is going to operate a decryption algorithm now. So, the decryption algorithm is going to take the scramble text and the key, and it is going to output the plain text which sender has actually encrypted using the encryption algorithm. So, the reason this encryption mechanism is called symmetric encryption mechanism is that we have a symmetry that the same key is getting used both for the encryption as well as the decryption. So, before going into the formal description of a symmetric key encryption process, let us first try to understand the difference between a deterministic and a randomized algorithm. So, a deterministic algorithm, in a deterministic algorithm, the output is a deterministic function of the input. That means, if we consider the straight transition in the algorithm, inside the algorithm, then the flow from the input to the output is always a deterministic function. What I mean by this is, if I run a deterministic algorithm on an input x 100 times, I am going to get the same output y 100 times. I will not get different output. That means, the output y is a deterministic function of the input x. Whereas, in a randomized algorithm, the flow from the input to output is non-deterministic, and the flow is going to be decided by the value of random bit strings which are going to be generated inside the algorithm as part of the algorithm. That means, in a randomized algorithm, it is not guaranteed that if I call that algorithm with the same input again and again, it is not guaranteed that I am going to get the same output, and the output may depend upon the sequence of random bits which I am going to generate inside the algorithm, and depending upon the value of those random bits, what path I followed inside the algorithm. So, that is a very high level difference between a deterministic algorithm and a randomized algorithm. Now, let us see the syntax of a symmetric key encryption scheme. So, any symmetric key encryption scheme, which is also called as a cipher, is going to consist of 3 algorithms. The first algorithm is the key generation algorithm, which is denoted by gen, and this algorithm is not going to take any external input. What this algorithm is going to do is, as part of the algorithm, inside there will be some random bit strings which are going to be generated, which I denote by this particular notation. So, when I say when I write this notation that someone is tossing the coin, I mean that inside the algorithm random bit strings are going to be generated, and based on the value of that bit string, the output is going to be determined. So, the output of this key generation algorithm is a key denoted by the symbol k, and since it is a randomized algorithm, every time I run the key generation algorithm, I am bound to get a different output. I will not get the same output. The syntax that we use to denote the key generation algorithm is the following. We say that the key generation algorithm gen, it does not take any input. So, that is why the brackets are left as empty, because it does not take any external input, and it is going to output a key which I denote by k, and this k belongs to a larger set, this calligraphic k, which is the set of all possible keys which this key generation algorithm can output. And the important thing here is that since this algorithm is a randomized algorithm, that is why I do not say that the output of gen is assigned the value k. Instead, I say that the output of gen is going to take one of the possible value k from the set of all possible keys. I am not using the assignment operator, because it is not a deterministic function, it is a randomized function, it is a randomized algorithm. So, here this calligraphic k is the capital K is the set of all possible keys which your key generation algorithm could output. So, for instance, if we know that a key generation algorithm is going to output a 256 bit key, then I know that this calligraphic key is a set of all possible 256 bit strings, namely the key space k is 2 to the power 256. And as I said earlier, this key generation algorithm is going to be a randomized algorithm. The second algorithm in any symmetric encryption scheme is the encryption algorithm denoted as ENC, and it is going to take 2 external inputs, namely the plain text which the sender wants to encrypt, which is going to be a bit string which I denote by the symbol b, and the key k which the key generation algorithm would have output. And apart from these 2 inputs, it has an internal input, namely the internal random coins which are generated, or the random bits which are generated as part of this encryption process, and as a result this encryption algorithm is a randomized algorithm. So, based on the message, the key space and the random bits which are generated inside the encryption algorithm, the encryption algorithm is going to output a ciphertext denoted as C. So, as I said that since the encryption algorithm could generate internal random bits to decide the outcome C, it is a randomized algorithm. And the syntax that we use to denote the encryption algorithm is the following. We say that the encryption of the plain text m. So, within the brackets I am writing the message m as the input, that means that is the external input which this encryption function takes as input, and the key k is put as a subscript. So, I will say that the message m is encrypted under the key k, and since this algorithm is a randomized algorithm, I am not using the assignment operator to denote the output of this encryption algorithm. Instead, I am saying that the output of this encryption algorithm is going to be one of the possible ciphertext from the set of all possible ciphertext which your encryption algorithm could produce. So, since this encryption process is a randomized algorithm, what it means is that even if I call this encryption process with the same value of m and the same value of k multiple times, I am going to get different ciphertext, because every time I call this encryption process, the set of random bit strings which are generated as part of the algorithm will be different. And since C is going to be a function of both the message, key and the internal random bits, the value of C will be different for different invocations of C. So, that is the syntax of encryption algorithm. Now, the decryption algorithm takes the ciphertext C as the external input and the key k which has been generated by the key generation algorithm, and in return it produces the plain text m. So, the syntax that I follow to denote the decryption algorithm is the following. We say that decryption of the input C. So, here C is the external input which is fed to the decryption function along with the key k. So, I will say that the decryption of the ciphertext C under the key k is going to produce the message M, and the message M belongs to the larger set of possible plain text, namely capital M, which is the plain text space. Now, notice that my decryption algorithm here is a deterministic function. There are no random bit strings which are generated inside the decryption algorithm to decide the outcome M, and as a result of that I am not using the notation arrow notation to denote the outcome of decryption. Instead, I am using the assignment operator to denote the outcome of the decryption function. What I mean by that is, if I call the decryption algorithm multiple times with the same value of k and the same value of c, I am bound to get the same M again and again. I will not get different M for the different invocations of DEC on the same value of c and k. In that sense, it is a deterministic function, and as a result we use the assignment operator to denote the output of the DEC function. So, that is the syntax of your key generation algorithm, encryption algorithm and the decryption algorithm. So, notice that we require the key generation algorithm and the encryption algorithm to be randomized, whereas the DEC algorithm should be deterministic. And there is a reason for that, which we will be able to appreciate when we discuss the various attack models in this lecture. Now, how to typically use a symmetric key cipher? So, imagine we have a symmetric key encryption scheme, namely we have a collection of key generation algorithm, encryption algorithm and decryption algorithm, and we assume that the steps of this key generation, encryption and decryption algorithm is publicly known. That means, the steps are known even to the sender and the receiver or to any third party in this world. Now, to use this symmetric key cipher, what sender is going to do is, it is going to run the key generation algorithm, which is going to output one of the candidate keys, namely k, from the key space, and this key will be agreed upon with the receiver by some magical mechanism at the beginning of the session. So, we imagine that at the beginning of the session, sender runs this key generation algorithm, and in that session there are several messages which sender would like to encrypt and communicate to the receiver using this key. So, the first step of the session will be the key generation algorithm and the agreement of that key with the receiver by some magical mechanism. Now, once the key is agreed upon, every time sender wants to encrypt a plain text M using this key, what is going to run is the following. It is going to run the encryption algorithm to produce the ciphertext, and the ciphertext will be communicated over the public channel, through which sender is communicated to the receiver. And as and when the receiver receives the ciphertext, what it is going to do is, receiver will be knowing what encryption process has been used by the sender. So, it will know the corresponding decryption process, and not only that, it will also know the key using which the sender has operated the encryption process. So, using the same key, it will operate the decryption process and will recover the plain text. That is how typically we are going to use a symmetric key encryption process. Now, what are the properties that we need from any secure encryption scheme or a secure symmetric key encryption scheme? So, roughly we need two properties. The first property is the correctness property, which says that for any key which the key generation algorithm has output, and for any plain text M which has been encrypted by M, the following condition should hold. If I encrypt the plain text M under the key k to obtain a ciphertext C, and if I decrypt that ciphertext C using the decryption process under the same key k, I should get back the original M. That is a correctness property. To give you the analogy, if you have a physical lock and if I have two copies of the key, what this correctness property demand is that if I actually lock that key using the key and send that lock in a locked condition to you, and if you have also the same key, and if you try to open that lock in the locked position using the key that you also own, you should be able to open the lock from the locked condition to the open condition. That is roughly the analogy you can imagine from this correctness requirement. The second important property which we need or expect from a secure symmetric key encryption process is that of privacy, and now we are going to see that what are the challenges we face when we try to formalize the privacy requirement. Intuitively, when we say that a symmetric key encryption process is secure or it achieves the privacy property, I mean that by seeing the ciphertext C, the adversary or the bad guy who has observed the ciphertext C should not be able to compute anything about the message M. That means, imagine there is a third party who is the bad guy who has intercepted the ciphertext, who knows the details of the key generation process, the encryption process and the decryption process. The only thing the bad guy does not know is the value of key with which the sender has operated the encryption process. The privacy property demands informally that even after this knowledge, the knowledge of ciphertext should not give any information about the message M. However, it turns out that if we want to formalize the privacy definition, there are several challenges that we face. So, what I am going to do next is I will propose a series of definition to formalize the privacy condition, and then we will see a potential loophole in each of these potential definitions, which is going to show you that how difficult it is indeed to come up with a right definition of privacy. So, my first candidate definition to formalize the privacy definition is the following. I will say that an encryption process is secure if the ciphertext does not reveal the underlying key. The intuition behind this definition is that if the key is revealed to the adversary, then it can find out any subsequent message which has been encrypted under that key. So, the minimum requirement which I require from any private encryption scheme is that the ciphertext should not reveal the underlying key. Well, it turns out that the requirement is definitely meaningful from any secure encryption process. This definition is completely useless. For example, consider an encryption algorithm which always outputs a ciphertext which is same as the plain text. That means, the ciphertext does not depend upon the key at all, and the value of the ciphertext is the same as the plain text. If you see this definition and this candidate encryption process, definitely the encryption process is not revealing anything about the key, and as per this definition you can label this encryption algorithm as a secure encryption algorithm. But this kind of encryption algorithm is completely useless to use in practice, because it is completely revealing your plain text. So, now let us rectify this definition and let me come up with the second candidate definition to formalize the privacy definition, and my definition 2 is I will say an encryption process is secure if the ciphertext does not reveal anything about the underlying plain text, because that is what is the basic intuition of the privacy. The problem with this kind of definition is, what do you mean by ciphertext does not reveal the underlying plain text? How much it should reveal, how much it should not reveal. For example, you might have an encryption process where 99% of the plain text is not revealed by the ciphertext, but unfortunately the ciphertext might be revealing 1% of the plain text, and that 1% of the plain text which is getting leaked by the ciphertext might be the critical information which you want to hide. Again, this definition and this candidate encryption process might look like satisfying the definition 2, but actually such kind of encryption algorithm I cannot use in practice. The problem with this definition is I am not exactly specifying what it means by revealing and not revealing, and how much to reveal and how much not to reveal. So, to fix this definition, let me propose the third definition, potential definition to formalize the privacy definition. The definition 3 says that an encryption process will be considered as secure if the ciphertext does not reveal any character of the underlying plain text. So, this will take care of the potential bug which was there in our definition 2, or the candidate encryption scheme that we proposed to violate definition 2, because now even if 1% is revealed, it is not going to satisfy definition 3. But again, there is a potential loophole in this definition. Consider an encryption algorithm where ciphertext does not indeed reveal any of the underlying characters of the plain text, but the ciphertext might reveal the range of the plain text, namely it might reveal whether the plain text is less than a particular threshold or whether it is greater than a particular threshold. Again, if I view the definition, this candidate encryption scheme indeed satisfies the property, because no character of the underlying plain text is revealed, but what is getting revealed is whether the plain text is less than a certain value or greater than a certain value, and that might itself be a security breach. So, I cannot afford to use such kind of encryption algorithm to encrypt sensitive data, because if the ciphertext is going to reveal the range of the sensitive data, I might be in trouble. So, let us try to fix this potential problem in definition 4, and the definition 4 says that an encryption process will be considered as secure if the ciphertext does not reveal any meaningful information about the underlying plain text. That means not only it should hide not only the underlying plain text, it should also hide whether the message is less than a certain value, greater than a certain value, and so on. Well, intuitively this definition is good, but the problem here is what exactly constitutes a meaningful information varies from application to application. For certain application, the underlying characters of the plain text might be the sensitive information. For another application, whether the message is less than a certain value or greater than certain value, that might be the meaningful information, and so on. So, you cannot exhaustively list down what constitutes a meaningful information for a particular application. That is the downside of this definition. So, that is, as a result, I cannot take it as a meaningful definition of privacy. So, to fix that problem, let us come up with the next possible definition of the privacy, and this definition says that an encryption process will be called as secure if the ciphertext does not help the attacker to compute any function of the underlying plain text. That means, imagine an attacker who has seen the ciphertext, who knows the encryption process, and the attacker is interested to compute some function, say f, of the underlying message which sender has actually encrypted in the ciphertext. We will say that the encryption process is secure if, using the knowledge of the ciphertext, adversary is not able to compute the function of the underlying message. Well, this is precisely what we expect from a secure cipher, but still there are certain loopholes in this definition. Namely, there are two loopholes. The first loophole is that how do you formalize whether a particular ciphertext has helped the adversary to compute a function of the underlying plain text or not? How do you judge that? How do you mathematically formalize that? That is the first loophole in this definition. And the second loophole in this definition is what exactly are the capabilities of the adversary you are considering. That is not specified in this definition. That means whether you are considering an eavesdropper adversary who is simply observing the ciphertext and trying to compute the function, or whether you are considering an adversary or malicious adversary who could change the contents of the ciphertext and see the behavior of the response of the receiver and then trying to compute the functions of the underlying messages. Also, this definition does not specify is the adversary also provided with any kind of additional information. That means, what are the various capabilities of the adversary which you are considering. So, even though intuitively definition 5 is the right definition, the two potential shortcomings of this definition is the exact formalization of whether the ciphertext is helping the adversary to compute any function of the underlying plain text, and what precisely is the attack model or the adversarial model you are considering. So, that brings us to the discussion of various attack models which we consider in the cryptography. So, typically in cryptography we consider the following 4 attack models. The first attack model is the ciphertext only attack or the COA attack model. The next attack model is the known plain text attack model or KPA model. The next attack model is the chosen plain text attack or CPA model, and the final attack model is the chosen ciphertext attack model or CCA attack. In all these attack models, the scenario is the same. We have a sender and a receiver who have agreed upon some common key by running the key generation algorithm and agreeing the key with the other entity by some magical mechanism, such that the adversary or the bad guy or the attacker is not aware of the key, and the adversary has intercepted some ciphertext, and the goal of the adversary is to compute some function of the underlying plain text which has been encrypted in this C. What differs in these attack models is the power of the attacker. That means, what kind of additional information apart from the ciphertext is available to the attacker. So, what we are going to do next is we will go through each of these attack models and see what are the capabilities of the attacker. So, let us start with the ciphertext only attack model or the CO attack model, which is the simplest possible attack scenario. And here the scenario is the following: we have the sender and the receiver who have agreed upon a common key not known to the attacker, and sender has encrypted several messages using the same key as per the encryption process, and the details of the encryption process is known to the attacker. The attacker has eavesdropped and intercepted those ciphertext. So, attacker does not have to do anything fancy here, it just have to listen over the channel what ciphertext contents have been communicated. So, that is why this attack is passive in nature, and the goal of the attacker here is to compute some functions of the underlying plain text. So, apart from the ciphertext knowledge, no additional information is available to the attacker in this attack model. The next attack model is the KPA attack model, which is slightly stronger attack model than the COA attack model, because here the adversary is available with some additional information compared to the previous model. So, the additional information which is available to the adversary is the following. The adversary is available with a collection of messages ciphertext pair, namely message M1 C1, message M2 C2, message MT CT. That means, it got a database of several message ciphertext pair, where each of the ciphertext in the pair is an encryption of the corresponding message in the pair under the same unknown key. That is important here. All the messages and the ciphertext are under the same unknown key, which is not known to the attacker. Now, you might be wondering how exactly it is possible for an attacker to come up with such pairs of message ciphertext in real life. So, there could be several scenarios through which it is possible for an attacker to get access to such message ciphertext pair. For instance, all encrypted messages do not remain private indefinitely, or if you consider the messages to be email exchange, then the first message in any email is usually the message hello, dear, hi, etc. In that sense, the encryption of certain messages under the unknown key is going to be revealed to the attacker. So, in this attack model, we assume that attacker has already got a collection of several message ciphertext pairs, and now a fresh message has been encrypted by the sender under the same key K and communicated over the public channel, and the goal of the attacker is to compute some function of this message M using the help of the ciphertext. I stress that the fresh message which is now getting encrypted by the sender might already belong to the collection of messages and ciphertext pairs which adversary possess. And this shows the importance of your encryption process to be randomized. So, recall when we discussed the syntax of symmetric key encryption process, I stressed that the encryption process should be randomized. That means, even if I encrypt the same message under the same key, I should obtain a different ciphertext. If you do not use a randomized encryption process, but instead use a deterministic encryption process, and if the same message is getting encrypted multiple times, then just by observing whether the ciphertext gets repeated over the channel, adversary could come to know whether the same message is getting encrypted or not. In this specific case, if the fresh message M which sender is actually communicating to the receiver is already present in the list, and if my encryption process is a deterministic encryption process, then this C is going to be already present in the list of message ciphertext pair, and adversary could easily find out the exact contents of the fresh message. That is why I need my encryption process to be a randomized encryption process. So, that is the KPA attack model. And as you can see, this is a more powerful attack model, because not only the adversary is available with the encryption of the message M, he is also available with the encryption of several earlier messages, and there he is already available with the encryption of several prior messages under the key K. The next attack model is a more powerful attack model, and this is called the chosen plaintext attack model or the CPA attack model. The scenario here is the following. We have a common key K agreed upon between the sender and the receiver by some magical mechanism, and now we assume here that the adversary gets an encryption oracle service to the encryption box. What I mean by that is the adversary can force or it can influence one of these two parties, say for example the sender, to encrypt any message of adversary's choice under the key K, and importantly, the sender who is actually providing the encryption oracle service won't be aware that actually it is encrypting messages of adversary's choice and providing those ciphertext to the adversary. So, that is why we say or we model this kind of service as an encryption oracle, because adversary won't be knowing the value of the key, but still it will be able to get or see the encryption of messages of any of its choice, of any message of its choice under that unknown key, and it can get the encryption oracle service for any number of message as long as it is polynomially bounded or it is practical in nature. That means, it should not be possible for the adversary to get the encryption oracle service for an infinite amount of time. He should be able to get encryption oracle service only for a limited amount of time or for a practical amount of time. So, we assume that it gets or it interacts with the encryption oracle service and submit messages of its choice, the plain text of its choice, and sees the corresponding ciphertext, and it builds upon a dictionary of messages ciphertext pairs. In this particular case, the message M1 C1, M2 C2 and the message MT CT, where all the ciphertext are the encryptions of the corresponding messages under the unknown key K. So, the kind of information that is available to the attacker here is same as in the KPA, namely in KPA model also adversary was provided with several message ciphertext pairs under the unknown key K, and here in the CPA model also adversary is available with several message ciphertext pairs under the unknown key K. The difference here is the messages in the adversary's database in the CPA model is now under the control of the attacker. That means, if adversary, depending upon the context of the underlying application, is already aware that these are the potential messages which sender might encrypt in the future, the CPA model allows the adversary to see encryption of those messages in advance by getting an encryption oracle service, right. Now, you might be wondering that how in reality it is possible for an adversary to influence the sender that please encrypt these messages for me without actually sender knowing that she or he is providing the encryption oracle service to the attacker. When we will be discussing the CPA attack model in some of our subsequent lectures, we will see how in reality it is possible to launch CPA attack. So, now assume that adversary is already available with this message ciphertext pairs. The goal of the adversary is the following: a fresh message has been encrypted by the sender under the same unknown key K and has been communicated over the cipher open channel to the receiver, and adversary has intercepted this ciphertext, and the goal of the attacker is to compute some function of the message which has been encrypted in this fresh ciphertext. I stress here that the message which is freshly encrypted might already belong to the database of message ciphertext pair which adversary possesses. I also stress that this CPA attack model is active in nature. That means, to get this encryption oracle service, the adversary not only has to listen over the public channel between the sender and the receiver, it also need to change the contents of the ciphertext which are getting communicated between the sender and the receiver and see the response of the receiver or the sender to get the encryption oracle service. That means, this particular type of attack is no longer an eavesdropping attack, this is now an active attack. So, that is the CPA attack model for you. Now, let us go to the next attack model, which is the strongest possible attack model, which we call as the CCA attack model, and here adversary can now get two kind of oracle service. It has got access to the encryption oracle service, that means it can ask for encryption of any message of its choice by influencing the sender or the receiver, plus it can get the decryption oracle service as well from any of the two parties, say for example from the receiver. What I mean by the decryption oracle service is that it can submit any ciphertext of its choice, because the adversary might be already aware that what could be the candidate ciphertext that your encryption and decryption that your encryption process might produce. So, it can come up with any candidate ciphertext and submit it to the it can influence the receiver to decrypt those ciphertext for the adversary, and in response the receiver is going to decrypt those ciphertext and send back the corresponding plain text back to the adversary. In that sense, we say that the adversary gets access to the decryption oracle, and there is no restriction on the order in which the adversary could get the encryption and the decryption oracle service. It could see or it could ask for the encryption oracle service for certain number of steps, and then it could ask for the decryption oracle service for certain number of steps, and there is absolutely no restriction on what messages he could get encrypted under the encryption oracle, and there is absolutely no restriction on what ciphertext it could get decrypted from the decryption oracle. So, we make no such restriction. And now adversary has two kinds of database. So, the first database is what it gets from the encryption oracle service. So, this is nothing but the encryption of several messages of adversary's choice under the key K, and the second database is the decryption of several candidate ciphertext of adversary's choice and the important thing here is that all the encryptions and decryptions are done under the same unknown key k. That is important here. So, adversary is now more powerful here, and the goal of the adversary is the following, that now imagine sender has a fresh message which has been encrypted and the adversary eavesdrops the ciphertext C. The goal of the adversary is to compute some function of the underlying plain text M with the help of the database that adversary has already prepared. I stress that the fresh message which sender is sending might already belong to the list database that adversary produced. The goal of the adversary is to compute that message M which has been freshly encrypted using the help of the database that is available to the attacker. So, these are the 4 attack models which we consider in the literature. Now, when I say that a particular encryption scheme is secure in a particular attack model, for example, if I say that an encryption scheme is secure in the CCA model, by that I mean that even if an adversary is launching a CCA attack, that means adversary got access to the encryption oracle service, it got access to the decryption oracle service, still it should be difficult for the adversary to compute any function of the underlying plain text which has been freshly encrypted and communicated over the channel. In the same way, if I say an encryption process is secure in the COA model or the ciphertext only attack model, I mean that just by looking into the ciphertext, adversary should not be able to compute any function of the underlying plain text, right. So, these are the 4 attack models which we will discuss in this course rigorously. Now, the final thing which I want to discuss for this lecture is the Kirchhoff's principle. So, definitely to maintain the security, the key with which the encryption and the decryption process are operated should be a secret, because if the key is leaked to the adversary can definitely find out what has been encrypted or decrypted. Now, you might be wondering, what about the encryption and decryption algorithm? Will I get more security by keeping the encryption and decryption algorithm private too? Well, as in cryptography, we strictly say that we should not follow this principle, and this is coming from a well known principle which we call as Kirchhoff's principle. So, Kirchhoff was a well known 19th century Dutch cryptographer, and he laid down several guidelines which should be followed by any good practical secure cipher. And one of the guidelines states that a crypto system should be secure if everything about the system is public knowledge except the key. That means what this principle clearly states, that the secrecy of the system should only rely on the secrecy of the key and not on the secrecy of the encryption and decryption process. Now, what is the importance of Kirchhoff's principle? What I mean by that, what are the arguments in the favor of Kirchhoff's principle? So, the first argument in the favor of Kirchhoff's principle is the following: maintaining the privacy of a key is a relatively easier task compared to maintaining the privacy of a pair of algorithm, because keys are roughly of size 100 bits, 200 bits, whereas programs are of 1000 times larger than the size of the key. So, that is why maintaining the privacy of a key is relatively an easier task than maintaining the privacy of a large algorithm. Also, the algorithm can be leaked or reverse engineered. That means, even if you assume that the encryption and decryption process which are operated by the sender and receiver are private, just by launching a KPI attack where adversary gets access to several messages and ciphertext pair, adversary could reverse engineer the steps of the encryption and decryption process. Also, another argument in the favor of Kirchhoff's principle is that if your key is leaked, it is very easy to replace a key, right, because your keys are of very short magnitude, right. Whereas, if a program is leaked, then it is, or if your encryption process is leaked, then it is very, very difficult to come up with a substitute, because as you will see in this course, coming up with new encryption algorithm is really a very challenging task. Also, it is infeasible to imagine a scenario where a user selects a pair of secret encryption and decryption process for every party with which it want to do the secure communication. For example, if I want to do secure communication with 100 parties, I cannot come up with 100 secret algorithms or 100 secret encryption algorithms for each of these users. Whereas, it is feasible to imagine that I am going to use the same encryption and decryption process with each of the 100 users, but I am going to use 100 different keys for operating each of these instances of encryption and decryption algorithm. And most importantly, if your encryption and decryption algorithms are publicly available, they go through public scrutiny, and if something has been proved to be secure even after they are existing for last 30-40 years, then we have a strong confidence that indeed those published algorithms are more secure compared to an algorithm about which you do not know any details, right. So, the summary here is it is extremely dangerous to use any kind of proprietary encryption process. So, if someone says that, hey, I am not going to leak the description of my encryption process, but I give you the guarantee that it gives you a very good amount of security, you should not believe such encryption process, because you do not know what kind of loopholes might be present in such an algorithm. So, it is always recommended to go or use algorithms which are available in public domain and has been scrutinized publicly. So, that brings us then to the end of this lecture. To summarize, we discussed the various types of cryptographic primitives that we use in cryptography. We also discussed the syntax of symmetric encryption process, and we focused on the importance of the key generation algorithm and the encryption algorithm to be randomized, because this comes as an implication of Kirchhoff's principle, which says that the secrecy of the whole system should rely on the fact that only the key is hidden, not the algorithms. Right. We also discussed the various kinds of attack models, namely the COA attack model, the KPA attack model, the CPA attack model and the CCA attack model. I hope you enjoyed the lecture. Thank you.